Hi, in this video, we're going to talk about how to describe the hybridization process for molecule with multiple bonds in it. We have learned how to describe the hybridization process for central atom. And then in the case of molecules with multiple bonds, it's going to be slightly more complex in terms of the process, because you need to explain as well the terminal atoms that has multiple bond attached to it. Having said that, you don't have to worry, because the scheme of work, the process of doing it through ground state, excited state, and hybridized states will be exactly the same. Okay, but the only thing that we need to look for and to be careful over here is when you want to draw the pi bonds, because when we are drawing pi bonding, it will be involving pure orbital instead, and we're not going to be using the hybrid orbital. So we're going to look into that one as we go further into this video. Right. As usual, before we want to go and describing the hybridization process, the first thing you need to do is you need to identify, okay, so you need to know what is the Lewis structure and the molecular shape for the given molecule. In the first example, we're going to look at carbon dioxide, and when you work out the Lewis structure and molecular shape for carbon dioxide CO2, you're going to get something like this, okay? And before we're going to go forward to find out how many unpaired electrons, the ground state, the excited state, and hybridized state, it's better for us to do a very simple prediction. We want to know what type of hybridization involved in the central atom carbon over here. And like I said, when you have terminal atoms with multiple bonds attached to it, right now, you also need to explain or describe the hybridization process for the terminal atoms, okay? So for carbon, we do know that it will have 1 and 2 sigma bonds. And for a multiple bond like this, a double bond, it will have pi bond right over here and another pi bond right over there. So that means you have 2 pi bond, okay? And to identify the type of hybridization, we only need to consider the sigma bonds. Why we only need to consider sigma bonds? Because, like I said earlier, that only sigma bonds will be involved in the hybrid orbitals overlapping. And for the pi bonds over here, they're going to be using pure orbitals instead, okay? So when you look at your central atom carbon, it does not have a lone pair, okay? You have 0 lone pair over here. So what can you conclude? You will have 2 lobes. So when you have 2 lobes, the hybrid orbital for carbon is sp hybrid orbital, and the shape for sp, we know that it's going to be like this, okay? What about oxygen terminal atoms? Both of them are identical, okay? So they are the same. So it's sufficient for you to just do one explanation or prediction over here, because whatever you're going to do for that one, it will be the same for this oxygen over here, because like I said, they are identical. When you look at your oxygen atoms, it has 1 sigma bond, and it has 2 lone pair, okay? Therefore, that one will be 3 lobes. So for this oxygen, the hybrid orbitals will be sp2. So that is the hybrid orbital involved for the oxygen terminal atom, and the shape for sp2, we all know that it's going to look something like this. So it's going to be the same for that oxygen atom because, again, I repeat, this oxygen is identical with that oxygen over here. Okay, now we have done our prediction. Now we can roughly imagine that the shape of the hybrid orbital for carbon is going to be sp, like that. And the shape of the hybrid orbitals for oxygen is going to be like that because this is sp2 hybrid orbital. Next, what we're going to be doing is we want to know how many unpaired electrons are involved in the formation of the molecules or the overlapping of orbitals. The reason why we want to know how many unpaired electrons, because later when we move on to the step where you're going to do ground state, excited states, hybridized state, we want to know whether we need to excite electrons or otherwise. Okay, so at this stage, for you to identify or to find out how many unpaired electrons are involved, we are going to be considering sigma bonds and pi bonds because they are the one that will be forming the covalent bonds that we want to be doing for carbon dioxide. Okay, so for this central atom carbon over here, it has 1, and 2 sigma bonds. Okay, and then it has 1 and 2 pi bonds. So how many unpaired electrons? We need 4 unpaired electrons. Okay, so what about each of the oxygen? So when you look at the oxygen right here, you have 1 sigma bond and 1 pi bond. Okay, so it is misconception for you to do 1, 2, 2, 1, 2, 2 right here. That is wrong, okay? Because this is a different oxygen terminal atom. That one is another oxygen terminal atom, but they are identical. Okay, so we have 1 sigma bond, 1 pi bond. Therefore, for the oxygen terminal atoms, we're going to have 2. We need 2 unpaired electrons. Okay, so I'm going to write a notes over here. So for this, needs 2 unpaired electrons for sigma overlapping in bracket head to head with the oxygen just now, sp3 orbital of oxygen. And then needs 2 unpaired electrons for pi overlapping in bracket sideway with sp orbital of carbon. So that is a very important note, very important note, because we want to know how many orbitals are involved in the mixing of pure orbitals to form the hybrid orbitals, and how many will be left behind unhybridized to form the pi bond. Okay, the same goes to the other side. Over here, it will need, as you can see, you have 1. Okay, you have 1 there. Needs 1 unpaired electron for sigma overlapping head to head with sp orbital of carbon. So you can double check. So yes, you have sp over here, sp orbital for the carbon, then sp2 for the oxygen, and we'll need one pi bond, one unpaired electron for pi overlapping bracket sideway with two p pure orbitals of carbon. So I'm gonna do a correction over here. So that is my mistake. So it is not sp orbital of carbon. Okay, so this is wrong. So what they will be doing needs two unpaired electrons for pi overlapping sideway with 2p pure orbitals of oxygen atoms. Okay, so that's about right. Now, it's very important as well that I have told you before in the previous video that you need to identify what is the valence electronic configuration for carbon and oxygen in order for us to be able to explain the ground state, excited states, and hybridized states before we're going to draw the overlapping. And as you can see, so that is the valence electrons for carbon, and these are the valence electrons for oxygen. So that is also very important. Now we're going to look at step 2, when we want to describe the ground state, excited state, and hybridized state. So remember, we need to use the valence electronic configuration for this. We have 2s over here, and then we have 2p right over there. So 1, 2. So that is the ground state electronic configuration, valence electronic configuration for carbon. So as you can see over here, it has only 2 unpaired electrons, but we have identified just now it needs, here, as you can see, it needs 4 unpaired electrons. Okay. So what we have to do next is we're going to try to excite one of the electrons from 2s orbital into that empty orbital right over here. Then you get something like this. So this electron is initially that electron, but it has been excited to that empty orbital to have 4 unpaired electrons. Now, just now we have talked about, so we have talked about it has 2 sigma bonds, and then you have 2 pi bonds for the carbon in CO2, for CO2. So when you have two sigma bonds over here, you only need to mix 1 and 2. So you have 1, 2. So you mix that 1s and 1p. You get sp hybrid orbital. So these are the only two unpaired electrons you're going to be using for the sigma overlapping. Okay. And then the other two right over here. So you have 2 remaining over there. So you have 2p. This one will be unhybridized for pi overlapping. Okay, so it's important for you to write that statement here as well. Okay, so you have 1, 2 for 2 sigma bonds, and then 1, 2 over here for 2 pi bonds. Okay, so when we look at the shape, sp is this, so that is the shape for carbon at CO2. So it's gonna look like this. You have sp here and sp there, and then you have 1 and you have 1. Okay, so you have 1 each unpaired electrons in the sp orbitals, and then remember you have this is your 2p, the one that is unhybridized just now, 1 unpaired electron, and you have another one over here. So this one is also 2p, 2p. Okay, 1 unpaired electron, and in the middle, that is your carbon. Okay, so what about oxygen? So we have to do the same step 2 for oxygen atoms, because it has a multiple bond, and therefore you need to describe the hybridization process. You have 2s, 2p, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and 8. And when you go back to your initial investigation, we have identified that the oxygen atoms needs 2 unpaired electrons. And when you look here, yes, you have 2 unpaired electrons. Okay, but for CO2, the oxygen has 1 sigma bond and 1 pi bond. So you only need 1 unpaired electrons over here, and you do remember just now in the hybrid orbitals you need to involve the lone pair. So nothing will need to get excited, okay, because you have 2 unpaired electrons over here is what you have predicted just now. You have this 1 lone pair, 2 lone pair with that 1 unpaired, so you're going to mix 1, 2, 3. You have sp2, so that is 1 lone pair, the second lone pair, and 1 unpaired electron for sigma overlapping, and then you have 1 unpaired over here, so that is 2p, pure 2p orbital, and that one will be unhybridized for pi overlapping. Okay, so to be safe, it's just better for you to redraw that one for the excited states. Although you don't have anything to be excited, to get excited, because we already get the 2 unpaired electrons right over there. Right, so for sp2, the shape is going to be that one. Okay, so that is for the oxygen. So we have it like this. The shape is sp2. So what we're going to be doing here is you're going to draw like that. Okay. So you have sp2, sp2, sp2. You have 1 electron being shared over here, and that is your sigma bond. And in these 2 lobes, you do remember we have 1 and 2 lone pair. So those are the lone pair. Okay, so you're gonna put the first lone pair and the second lone pair. Okay, and you have this one for pi overlapping. So you're gonna draw 1 here, like that. So this one is 1 electron, 2p and 2p. So what happened here, this 2 will be overlapping sideways. So that's how you're going to show sideways overlapping. You have 2 lines over here, but this 2 line is not representing 2 pi, okay? But you have one on the top and 1 at the bottom. So now you have 1. So this, you need to draw top and bottom to show that 1 pi orbitals, okay? So this one over here is for that one. Okay, so that is a misconception students always have. They think that when you do 1 here, that is 1 pi. When you do 1 there, that is another 1 pi. No, when you have 1 top, 1 bottom, that is 1, representing 1 pi, 1 pi bonds, okay? Because you need to think your bond in terms of 3D. So you need to imagine that this orbital over here is enveloping that one. So you can imagine that, so this is like your sigma bond. Okay, so that is your sigma bond. And then what happened now, you have another like this. Okay, so inside your pi bond, you have your sigma bond. So that's why you have up and down there. Okay, so if you have a triple bond, then you have another one to envelop that one. Okay, so this is just a very convenient way to show that the sigma bond over here is enveloped by that one. Okay. Now, what about the other side? Okay, we have the other side over here. So before we're going to proceed, remember that one is your oxygen. Okay, so you have 2 lone pair for that one, 2 lone pairs. So we're done with this oxygen. What about on this side? You have 1. Okay. And 2. So you have 1 shed, so that is the sigma bond. So for that one, sigma bond. And don't forget to label your lobes, sp2, sp2, sp2. And you have 2 lone pairs, so 1 lone pair, 2 lone pair, And what about your pi bonds over here? So you have this, another one, you haven't drawn the overlapping. So you're going to draw it. The direction is going to be quite parallel to one another. So you have 1 here, 2p for the oxygen. So you're going to do the same thing. So you have above and below. So this is your pi bond, and that one is another pi bond. And don't forget, that one is your oxygen atom. So this is a complete drawing for carbon dioxide, okay? Or you can do it like this. So the molecular shape is linear and the angle is 180 degrees, okay? Next up is for this, when you have a triple bond. So this one is going to be quite slightly different because you have more than one pi bond in a single multiple bond. Okay, as usual, what we need to do, we need to identify how many sigma bond, how many lone pair we want to predict. What is the type of hybridization will be involved, okay? Now you have your central atom, of course, it will be hybridized. So we have one sigma bond right over there. And obviously you do not have any lone pair. So that one is going to be, no, you have, that is incorrect. You have another sigma bond right over there. So you have 1 and 2 sigma bonds, 0 lone pair on your carbon. So you have 2 lobes. 2 lobes means you have sp, hybrid orbitals, and the shape is like this, okay? And what about your nitrogen? Your nitrogen has 1 sigma bond, okay, just 1 sigma bond over here, and 1 lone pair. Also, it will have 2 lobes, okay? So 2 lobes means you will have sp hybrid orbital for the nitrogen as well, okay? But what you can identify now, what you can see here, it has 2 pi bonds in between the carbon and that nitrogen atom. So you would be expecting to draw a sideways parallel pure orbitals to do the overlapping for pi bonding. Okay, so we need to find out what is the number of unpaired electrons involved in the formation of HCN in the overlapping of the orbitals. For carbon, carbon has 1, 2 sigma bonds and 1, 2 pi bonds. Here you have 4 unpaired electrons, okay? Right here for nitrogen, you have 1 sigma bond and 1 and 2 pi bond. So right there, you need 1, 2, 3. So you need 3 unpaired electrons, okay? So what we have done in the beginning, we have identified that this 2 unpaired electrons, 2 unpaired electrons for sigma overlapping, okay, for sigma overlapping, and then that 2 unpaired electrons for pi overlapping. So pi overlapping is sideways. Sigma overlapping is head to head. Okay, so same goes to here. You have one unpaired electron for sigma overlapping in bracket head to head, and you have two unpaired, okay, two unpaired electrons for pi overlapping. So pi overlapping is sideways. Okay. Now, so we want to know what is the valence electronic configuration. We have done this just now. For carbon, you have 1s2, 2s2, 2p2, and that is the valence electrons you need to be using. For nitrogen, you have 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, and 7. So you have 2p3. And that is the valence electrons we need to consider when you want to show the orbital hybridization and overlapping. Now, step 2, so ground states of carbon. So ground state of carbon, you have 2s, 2p, 1, 2, 3, and 4. From the analysis that we have done just now, we need to have 4. Okay, we need to have 4 unpaired electrons. If you go back here from the analysis, we have identified that you need to have 4 unpaired electrons for carbon. Over here, you have only 2 unpaired. So what we need to do? Yes, we need to excite one of the electrons from 2s orbital, and you get your 4 unpaired electrons. Okay, but you need to know how many orbitals you need to hybridize. Remember, for HCN, it has 2 sigma bonds and then 2 pi bonds. Therefore, you only need to mix S and 1 P. Okay, you only need to mix 1 S, that one over here, and that 1 P, right, one over there, to get sp hybrid orbitals. So those are the 2 unpaired electrons you're going to be needing for sigma bond overlapping. And then the other 2 unpaired electrons over here, that one is 2p. This one will be left unhybridized for pi overlapping. Okay, so it's kind of like similar to what we have done in the beginning for carbon dioxide. So remember, from your analysis, it's very important for you to get all the analysis correctly. When you reach this point, that will serve as a reference points. Okay, so let's have a look again. So that is the shape, okay, for carbon. If we look here, carbon sp just now. So you have something like this. So this is sp. Don't forget to label that sp. And then one unpaired electron and another one unpaired electron right there. And we have 1 and 2. Okay, we have 1 and 2. Pi bond. Okay, you have one like this, 2p, 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 1. And then we have another one like that, 2p, 2p, 1 unpaired electrons. Okay, so the one in blue, that one is for the sigma bond overlapping, and then the one in yellow over here for pi overlapping, and also the one in green over here, pi overlapping. Look at that one. So those are the pure 2p orbitals of carbon. Okay, so don't forget to, that one is going to be your carbon right there. Okay, so what about, so what you can do now over here, you can do for hydrogen. You can already do for hydrogen right there. Okay, so hydrogen always gonna be using its 1s orbital for overlapping. Now you've got one sigma bond right there. So that is the sigma bond that we have drawn. And we are left with the one here, nitrogen. So let's go back. For nitrogen, you have 2s, 2p, 1, 2, 1, 2, 3, 4, 5, 6, and 7. So we have identified just now nitrogen needs only 3 unpaired electrons to form the overlappings that it needs to be doing with carbon's central atom. And at the ground state, as you can see, you have 3 unpaired electrons already. So you don't have to excite anything else. But it's very important for you to always remember that you have, just now you have 1 sigma bond and 2 pi bonds. Okay, so 1 sigma bonds means you need to have 1 unpaired electron in the hybrid orbital. So what we're going to be doing here, so you have 1s and 1p, sp. So you have this. So this is the one that will be forming the lone pair, and that one will be forming the overlapping of sigma bond with carbon later on. So we have mixed 1 and that together, and you have this 2, 1, 2, 2p. So this one is unhybridized for pi overlapping. Okay, so you have 2. Okay, so sp, the shape for sp is like this. So that one is sp orbital, sp orbital. You have overlapping over here. You can do it like that. And remember, you have 1 lone pair. And when you look at the explanation over here, you have 1 lone pair over here. And don't forget here to just rewrite the same thing, because you don't excite anything for nitrogen in this case. Okay, so remember that is your lone pair. So your lone pair, this lone pair will be in that sp hybrid orbitals. And we have two. We have one pi bond, so we're going to draw it like this, parallel to that, 2p, okay, 2p. And then the other one is going that way, also 2p, and you have that one. So this one is not complete yet. Why? Because you need to show this. You need to show sideway overlapping. So that is for this pi bond. And then 1, 2. So you have another overlapping over here. So those are for this pi bond. Okay. So don't forget to put your nitrogen here. So that is the complete drawing for HCN. So this is how you're gonna draw it very neatly and nicely. Okay, so the molecular shape is also linear and the angle is 180 degrees. Now let's have a look at another example. So over here we have HCOOH. The difference with this example with carbon dioxide, right now you have this oxygen and that oxygen are not identical. They are different oxygen because this oxygen over here is connected via multiple bond, and that oxygen over here has only one single bonds attached to it. So those oxygens are two non-identical oxygen. So yes, you need to have 3 explanation for the GEH, okay? But it's the same thing. So first we're going to try to guess what is the type of hybridization. At the carbon atom over here, you have 1, 2, and 3. Okay, 3 sigma bonds, and obviously carbon does not have a lone pair. So in this case, you're going to have 3 lobes, and 3 lobes is sp2 hybrid orbitals, and therefore the shape of your carbon electron clouds or orbital is going to be like that. And then when you look at the carbon, that one, for the oxygen at C double bond O, okay, sigma bond, you have sigma bond here, 1 sigma bond, and then it has 2 lone pair. So this one also 3 lobes, and 3 lobes is sp2. So it has the same hybridization type with the carbon right there. But what about the oxygen that is attached to H and carbon? So it has 1 sigma bond, 2 sigma bond, and then 1 and 2 lone pairs, making that 4 lobes. So 4 lobes is sp3 hybrid orbitals. sp3 hybrid orbital is like that, the shape. Okay, so just a bit of work you need to do. More work you need to do. Again, now we need to know how many number of unpaired electrons. So we're going to start with carbon. Carbon has 1, 2, three sigma bonds. Okay, so this here is a pi bond. So pi bond is 1. So you need 4 unpaired electrons. So the oxygen right here, you have 1 sigma bond and 1 pi bond. So it needs 2 unpaired electrons. And this oxygen here, you have 1 sigma, 2 sigma, you have 2 sigma bond, 0 pi bond. Therefore, you need to have 2 unpaired electrons. Okay, so you do know what you need to have over here. It needs to have 3 unpaired electrons for sigma overlapping in brackets head to head. Okay, here it needs to have 1 unpaired electrons for sigma overlapping head to head. Over here it needs to have 2 unpaired electrons for sigma overlapping head to head, and 1 unpaired electron for pi overlapping sideways. This guy over here also need 1 unpaired electron for pi overlapping. So this one also sideways. This one no sideways. Okay, valence electron, carbon 1s2 to s2 to p2. So that is the valence electrons you need to have for both oxygen, regardless of the type. It's going to have the same valence electronic configuration, 1s2 to s2 to p4. So that is the valence. All right. Now, ground state. We have 2s, 2p, 1, 2, 3, 4, and it needs 4 unpaired electrons just now. So we're going to excite that. 1, 2, 3, 4. Okay, and it will be, remember, it will have 3 sigma bonds and 1 pi bond. So when you have 3 sigma bonds, you're going to mix 1 s and 1 2p orbitals. 1 2 3. So you have sp2. 1 pi bond. So you have 1 over here. 2p will be unhybridized. 4 pi overlapping. Okay, so the shape is sp2. Okay, sp2 is this shape. So your carbon, okay, your carbon is going to be looking something like, okay, so it's going to be looking like 1. Okay. sp2, sp2, sp2. Okay. And then if you look here, you have 1H. So you can draw the H over here. 1 S H. So you have that overlapping, sigma overlapping right there. And then you have this, okay, oxygen. Later on, you're going to try to identify, and also that one. Okay, so we have just now we have one unhybridized 2p orbitals. Okay, so that is your carbon. So what about the other? So don't forget your lone pair. We're gonna try to do for this one first. Okay, oxygen atom. Okay, we're gonna try to do for oxygen atom at C double bond O. It has 2s, 2p, 3, 4, 5, 6. From the analysis, we have identified that it needs to have one unhybridized 2p orbitals in order for it to be able to form the pi bond. Okay, so you don't have to do anything for the excitation. So remember, it needs to have 1 sigma bond and 1 pi bond. So 1 sigma bond, what happened here? You're going to mix 1, 2, 3. 1, 2, 3. So that one is sp2. 1, 2. So those are the lone pairs. Okay, those are the lone pairs. And 1 unpaired electron for sigma overlapping. And you have 1 2p unhybridized 4 pi overlapping. Okay, so don't forget this one. You just need to copy that one. You don't have to excite anything. Okay, remember those two are the lone pairs, and this one is going to be doing the pi overlapping. So let's go to the structure here. So the shape just now is sp2. Okay, so we're going to do one like this, like that. You have sp2, 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 and that one is the sigma bond for that. And you do need to remember that over here you have one lone pair and another one lone pair right there. And don't forget this one, 2p, 2p, F1 there. So this is the pi bond, that one. And what about the one here? So we're going to look at this oxygen. It has 2s, 2p, 1, 2, 3, 4, 5, 6, 7, 8. And you need to remember, it has 2 sigma bonds and 0 pi bond. So you need to have 2 unpaired electrons in the hybrid orbitals. Then you have to mix all of them, okay? So you have 1, 2, 3, 4. You have sp3 hybrid orbitals. So these two are going to be the lone pair, the first lone pair, second lone pair, and then that one will be another another sigma bond. This one, another sigma bond, okay, to form that. And don't forget this. You just need to rewrite the same thing. So sp3, the shape of sp3 is like this. So that is the shape we're going to draw. Here, I'm going to use green. So the shape of sp3 is something like 1, like that. Okay, so label sp3, 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 sp3. Remember, it has 2 lone pairs, 1 and 2 lone pairs. So the first lone pair, that one. And then the second lone pair, this one over here. Okay, and then you have that H. So you can put the H right there. So that is 1s H. Okay, another sigma bond. That's sigma bond. And another sigma bond right over here, which is that one sigma bond. So that is the shape. Okay, so that is the shape of the orbital overlapping. So that's how you're gonna draw it neatly.